Chapter 10 Use of Computer for Weight and Balance Computations Introduction. Almost all weight and balance problems involve only simple math. This allows slide rules and handheld electronic calculators to relieve much of the tedium involved with these problems. This chapter compares the methods of determining the center of gravity, CG, of an airplane while it is being weighed. First, it shows how to determine the CG using a simple electronic calculator, then solves the same problem using an E6B flight computer. Finally, it shows how to solve it using a dedicated electronic flight computer. Examples of typical weight and balance problems, solved with an electronic calculator, that pilots and airframe and powerplant, A&P, maintenance technicians encounter throughout their aviation endeavors are shown later in this chapter. Electronic calculator determining the CG of an airplane in inches for the main wheel weighing points can be done with any simple electronic calculator that has addition, plus, subtraction, dash, multiplication, times, and division divided by functions. Figure 10.1, scientific calculators with such additional functions as memory, parentheses, plus or minus, plus slash, exponential, x, reciprocal, 1 slash x, and percentage, percent, functions allow more complex problems to be solved or simple problems to be solved using fewer steps. According to Figure 10.2, the weight of the nose wheel, F, is 340 pounds, the distance between main wheels and nose wheel, L, is minus 78 inches, and the total weight, W, of the airplane is 2,006 pounds. L is negative because the nose wheel is ahead of the main wheels. To determine the CG, use this formula, CG equals F times LW 340 times minus 78 equals 2006. Key the data into the calculator and press the equals key. The answer should read as follows, 340 times 78 plus slash divided by 2006 equals, minus 13.2. The arm of the nose wheel is negative, so the CG is minus 13.2 or 13.2 inches ahead of the main wheel weighing points. E6B flight computer. The E6B uses a special kind of slide rule. Instead of its scales going from 1 to 10, as on a normal slide rule, both scales go from 10 to 100. The E6B cannot be used for addition or subtraction, but it is useful for making calculations involving multiplication and division. Its accuracy is limited, but it is sufficiently accurate for most weight and balance problems. The same problem that was just solved with the electronic calculator can be solved on an E6B by following these steps. CG equals F times LW 340 times minus 78 equals 2006. First, multiply 340 by 78, disregard the minus sign, figure 10.3. Step 1, place 10 on the inner scale, this is the index opposite 34 on the outer scale that represents 340. Step 2, opposite 78 on the inner scale, read 26.5 on the outer scale. Determine the value of these digits by estimating, 300 times 80 equals 24,000. So 340 times 78 equals 26,500. Then, divide 26,500 by 2006, figure 10.4. Step 3, on the inner scale, place 20, which represents 2006 opposite 26.5 on the outer scale, 26.5 represents 26,500. Step 4, opposite the index, 10, on the inner scale read 13.2 on the outer scale. Determine the value of 13.2 by estimating, 20,000 divided by 2,000 equals 10, so 26,500 divided by 2006 equals 13.2. The arm, minus 78, is negative, so the CG is also negative. The CG is minus 13.2 inches or 13.2 inches ahead of the datum. Dedicated electronic flight computer. Dedicated electronic flight computers, like the one in figure 10.5, are programmed to solve many flight problems such as wind correction, heading and ground speed, endurance, and true airspeed, TAS, as well as weight and balance problems. The problem just solved with an electronic calculator and an E6B can also be solved with a dedicated flight computer using the information shown in figure 10.2. Each flight computer handles the problems in a slightly different way, but all are programmed with prompts that solicit the required data to be inputted, so there is no need to memorize any formulas. Weight and arms are inputted as called for, and a running total of the weight, moment, and CG are displayed. Typical weight and balance problems. A handheld electronic calculator like the one in figure 10.5 is a valuable tool for solving weight and balance problems. It can be used for a variety of problems and has a high degree of accuracy. The examples given here are solved with a calculator using only the times, divided by, plus, dash, and, plus slash functions. If other functions are available on your calculator, some of the steps may be simplified. Determining CG in inches from the datum. This type of problem is solved by first determining the location of the CG in inches from the main wheel weighing points, then measuring this location in inches from the datum. There are 4 types of problems involving the location of the CG relative to the datum. Nosewheel airplane with datum ahead of the main wheels. The datum, D, is 128 inches ahead of the main wheel. Weighing points. The weight of the nosewheel, F, is 340 pounds, and the distance between main wheels and nosewheel, L, is 78 inches. The total weight, W, of the airplane is 2,006 pounds. Refer to Figure 3.5 on page 3.5. Use this formula. 1. Determine the CG in inches from the main wheel. 340 times 78 divided by 2006 equals 13.22. Determine the CG in inches. Form the datum. 128-13.2 equals 114.8. The CG is 114.8 inches behind the datum. Nosewheel airplane with datum behind the main wheels. The datum, D, is 75 inches behind the main wheel. Weighing points. The weight of the nosewheel, F, is 340 pounds, and the distance between main wheels and nosewheel, L, is 78 inches. The total weight, W, of the airplane is 2,006 pounds. Refer to Figure 3.6 on page 3.5. Use this formula. 1. Determine the CG in inches from the main wheels. 340 times 78 divided by 2006 equals 13.22. Determine the CG in inches from the datum. 75 plus 13.2 equals 88.2. The minus sign before the parenthesis in the formula means the answer is negative. The CG is 88.2 inches ahead of the datum, minus 88.2. Tailwheel airplane with datum ahead of the main wheels. The datum, D, is 7.5 inches ahead of the main wheel. Weighing points. The weight of the tailwheel, R, is 67 pounds, and the distance between main wheels and tailwheel, L, is 222 inches. The total weight, W, of the airplane is 1,218 pounds. Refer to Figure 3.7 on page 3.6. Use this formula. 1. Determine the CG in inches from the main wheels. 67 times 222 divided by 1,218 equals 12.22. Determine the CG in inches from the datum. 7.5 plus 12.2 equals 19.7. The CG is 19.7 inches behind the datum. Tailwheel airplane with datum behind the main wheels. The datum, D, is 80 inches behind the main wheel. Weighing points. The weight of the tailwheel, R, is 67 pounds, and the distance between main wheels and tailwheel, L, is 222 inches. The total weight, W, of the airplane is 1,218 pounds. Refer to Figure 3.8 on page 3.6. Use this formula. 1. Determine the CG in inches from the main wheels. 67 times 222 divided by 1,218 equals 12.22. Determine the CG in inches from the datum. 80 plus 12.2 equals minus 67.8. The CG is 67.8 inches ahead of the datum. Determining CG, given weights and arms. Some weight and balance problems involve weights and arms to determine the moments. Divide the total moment by the total weight to determine the CG. Figure 10.6 contains the specifications for determining the CG using weights and arms. Determine the CG by using the data in Figure 10.6 and following these steps. 1. Determine the total weight and record this number. 2. Determine the moment of each weighing point and record them. 3. Determine the total moment and divide this by the total weight. This airplane weighs 2,006 pounds and its CG is 114.8 inches from the datum. Determining CG, given weights and moment indexes. Other weight and balance problems involve weights and moment indexes, such as moment/100 or moment/1,000. To determine the CG, add all the weights and all the moment indexes. Then, divide the total moment index by the total weight and multiply the answer by the reduction factor. Figure 10.7 contains the specifications for determining the CG using weights and moments indexes. Determine the CG by using the data in Figure 10.7 and following these steps. 1. Determine the total weight and record this number. 2. Determine the total moment index, divide this by the total weight, and multiply it by the reduction factor of 100. This airplane weighs 2,006 pounds and its CG is 114.8 inches from the datum. Determining CG in percent mean aerodynamic chord, MAC, the loaded CG is 42.47 inches after the datum. Mach is 61.6 inches long. Lmac is at station 20.1. 1. Determine the distance between the CG and Lmac. 2. Then, use this formula. The CG of this airplane is located at 36.3% Mach. Determining lateral CG of a helicopter. For a helicopter, it is often necessary to determine not only the longitudinal CG, but the lateral CG as well. Lateral CG is measured from butt line 0, BL0. All items and moments to the left of BL0 are negative, and all those to the right of BL0 are positive. Figure 10.8 contains the specifications for determining the lateral CG of a typical helicopter. Determine the lateral CG by using the data in Figure 10.8 and following these steps. 1. Add all of the weights. 2. Multiply the lateral arm, the distance between butt line 0 and the CG of each item, by its weight to get the lateral offset moment of each item. Moments to the right of BL0 are positive and those to the left are negative. 3. Determine the algebraic sum of the lateral offset moments. 4. Divide the sum of the moments by the total weight to determine the lateral CG. The lateral CG is 0.77 inch to the left of BL0. Determining delta CG caused by shifting weights. 50 pounds of baggage is shifted from the aft baggage compartment at station 246 to the forward compartment at station 118. The total airplane weight is 4,709 pounds. How much does the CG shift? 1. Determine the number of inches the baggage is shifted. 2. Use this formula. The CG is shifted forward 1.36 inches. Determining weight shifted to cause specified delta CG. How much weight must be shifted from the aft baggage compartment at station 246 to the forward compartment at station 118 to move the CG forward 2 inches? The total weight of the airplane is 4,709 pounds. 1. Determine the number of inches the baggage is shifted. 2. Use this formula. Moving 73.6 pounds of baggage from the aft compartment to forward compartment shifts the CG forward 2 inches. Determining distance weight is shifted to move CG a specific distance. How many inches aft does a 56-pound battery need to be moved to shift the CG aft by 1.5 inches? The total weight of the airplane is 4,026 pounds. Use this formula. Moving the battery aft by 107.8 inches shifts the CG aft 1.5 inches.